Our first speaker is Mikael Slevinsky, and he'll be talking to us about robust and stable rational approximation of generalized hypergeometric functions.
Yes, thank you, and thank you very much for the invitation to this wonderful event. Complex analysis is so beautiful because if you take off the words fast and stable, rational approximation of generalized hypergeometric functions has existed for probably about 40 years. So it's amazing that you can still do something new every once in a while, even though some topics are amazingly old and wonderful. This is a joint work with my student, master's student Yuli at the University of Manitoba. So I'm actually more in a spectral methods person, and this is almost so venturing into the complex plane is sort of a means to an end. I've ended up in many sort of facets where I've encountered a wall, and that wall happened to be generalized hypergeometric functions, and I wanted reliable algorithms to work with those. And I apologize that they won't light up your brain as well as Riemann-Hilbert problems, but as a matter of fact, they are also building blocks for Cauchy transforms, and so they are somehow a little bit more fundamental, at least in the complex analysis part. So I build sort of software, and so I started with some PhD software with double exponential quadrature. Then for my postdoc, I went to singular integral equations. And then for sort of early career stuff, I'm working with fast orthogonal polynomial transforms. And so I'm hoping that, as you can see, there's like a nice progression in the number of stars. Hopefully, hypergeometric functions, this new package, has about 300 stars in a couple years. So, but who's counting, right? So here's the package. And if you load all of the packages for tomorrow's presentations by the master class, you'll actually already have hypergeometric functions. So it's really easy to add. Okay. All right. So let's get into it. So how do we do this? Okay. Right. Generalized hypergeometric functions are defined formally by their Maclaurin series. So they have a ratio of Pochhammer symbols, and it's an infinite sum, and they're defined so the Taylor series at the origin. They can sometimes be terminating if one of the coefficients in the numerator is a negative integer or 0, and it will terminate after that many terms. If it's not terminating, then I suppose there's many different sort of subcases, but the main breakdown is in terms of the radius of convergence. And so if p is greater than q plus 1, these are factorially divergent series, and we typically assign meaning to them as the asymptotic expansions of an integral. If p is equal to q plus 1, this is like the Gauss class, where they're analytic within the unit disk. And if p is less than or equal to q, they're entire, so think of them like e to the z. Okay. Right, so where do they appear? So a great place to start is with small p and q, so we'll start with 1f1. And so they appear in the so-called phi functions for exponential integrators. So if you take phi naught as e to the z and then recursively peel off the smallest term in the Maclaurin series, then you end up with these phi functions, and they're numerically unstable if you just write out the formula. But there's an algorithm to deal with them, and it couples well with the setting in exponential integrators where you're dealing with a linear operator, and it's to use Cauchy's integral formula. But they are a 1f1, so I just wanted to make that connection. Right? They actually also appear with choosing optimal parameters in ADI. So so for instance, the elliptic integrals, kz, and the Jacobi elliptic functions appeared in Alex Townsend's talk earlier in choosing those optimal parameters. And this kz is okay, it's this elliptic integral. It has an algorithm that cannot be beaten with anything I'm going to talk about today. But it's a very specific algorithm. It uses the arithmetic geometric mean between two numbers that converges quadratically. And lo and behold, they are a 2f1 up to some scaling. Polynomial filters have been used by Jared Arntz, a student of Yusuf Saad Kalansis and Yusuf Saad himself. to home in on a particular subset of a spectrum of an extremely large matrix, symmetric. So here, for instance, what we can do is we could take the Heaviside step function, and we have its infinite series in terms of Chebyshev polynomials. And this would actually sort of isolate the right half of the spectrum if it were in -1, 1 completely. So what's cool is that you can actually take the Chebyshev polynomials and write them as the real part of e to the I r cos of x, and then we can again identify a 2f1. So some of the hypergeometric functions that touched on work that sort of got me frustrated with the software was extent software was Stieltjes integrals of weighted Jacobi polynomials. So here, if you want to deal with, for instance, numerical solution of Riemann-Hilbert problems or polygonal scattering problems, although we've seen also very modern methods today with rational approximations, you can actually nail the singularities exactly as long as you use essentially a rather large dictionary of functions. But some of these would involve taking the Stieltjes integral or the log integral, which can be derived from this formula of weighted Jacobi polynomials, weighted with the orthogonality weight. And these are defined, they actually define Jacobi functions of the second kind, but that's almost tautological, so we might as well just say, actually, the right-hand side is equal to a 2f1. And that shouldn't be surprising because they satisfy the same differential equation. Okay. Actually, this is a bonus slide. So if you take those parameters to be -1/2, you actually get that the Cauchy transform, or the Stieltjes transform of weighted Chebyshev polynomials doesn't actually need to use a vanishing basis. So there's a lot of fun in using the approach of Wemp, McCabe, and Connor from 1997. Okay, just to say that we can actually end up with scenarios where P and Q are not necessarily less than 2, less than or equal to 2. So my student and I looked at one version of non-local diffusion, which is essentially from essentially the work of Chang, Du, and his collaborators. And it starts with trying to create a drop-in replacement for the local Laplacian, which gives our operator 2 knobs. One is a spectral knob, so this will determine sort of the angle of the eigenvalues, and then the other one will give us an ability to give it a kink in the spectrum. And so that's so the spectral knob is in terms of alpha, and then the kink is determined in terms of delta, which is the horizon of our kernel. So as long as we're working in RD, this operator is diagonalized by the Fourier modes, provided that our kernel is spherically symmetric. And then from there, we can actually show that this integral over RD can be actually written down in terms of an integral in one dimension over the radial sort of variable. And since J is actually a 0f1, when we peel off one of the terms, that will give us a 1f2, and then integrating that, we actually get a 2f3. Right? So the spectrum of this operator has a representation in terms of generalized hypergeometric functions, and it's not a particularly nice one to work with, right? The parameters are large, or P and Q are larger than 2, for instance. At least one of them is, yeah. This expression here actually runs out of steam, and the beautiful thing about hypergeometric functions is sometimes you can actually have all sorts of different expansions. And so the other thing we did is we took a look at when the modulus of the wave number multiplied by delta, this kernel sort of horizon, tends to infinity, and we got an asymptotic expansion, a full asymptotic expansion given in terms of Bessel functions and Lommel functions. And Bessel functions have nice sort of computational software, but Lommel functions don't. But fortunately, we can identify them as a 3f0, so they have a divergent asymptotic expansion. So there you go, 2 different versions of PFQs, and parameters are quite large. Okay, right. So this was just a small overview of areas where generalized hypergeometric functions appear. Beautiful algorithms exist for special cases. in particular the arithmetic geometric mean, this quadratic convergence, right? But it's all sort of specialized and ad hoc. So what can we say about the general case? Well, Frederick Johansen would say that rigorous computation should only use the Maclaurin series. But this is so suppose we can do a little bit better than that, right? So one of the issues with using a Maclaurin series is, okay, if you want to analytically continue, you might have to march with a Taylor series, and if you march in the neighborhood of possibly bad singularities, and since we haven't put any conditions on the parameters yet, we do have a branch cut, and in some of the hypergeometric functions, and if that branch point or the strength of that singularity is large, it might as well be an essential singularity, and marching around an essential singularity could lose you as many as 26 million digits, right, according to Trevethan. Right. So we're not going to do that. Solving the differential equation is hard. It's too technical, it's too complicated, and those are not my words, it's Johansen, that's in his paper, and near the singular points. It has been attempted by a multi-author paper starting with Crespo, only for 2F1, and here we benefit from, they benefit from the fact that near some of the parameters where log terms show up, you can remove some of the sort of logarithmic singularity with a single constant. But now you're working with a frame, and your approximation theory gets, again, far more complicated. When P and Q are substantially larger than that, there are more terms in the differential equation that could appear and totally surprise you. Okay, so the approach that I and my student propose is rational approximation, and that's not new. What we would like to do is take old algorithms and make them blazingly fast. Okay, so one alternative, and many people will agree is the gold standard, is to use Padé approximation, right? So one of the references on that is the book by Baker and Graves Morris, right? So naively, for a type KK approximant, which is when you get the most bang for your buck usually, the naive complexity is O of k cubed if you're solving a linear system. If you use a Hankel plus rank 1 structure, or perhaps you'll see it as templates depending on how you organize your coefficients, you can reduce it to O of k squared with the Levinson-Durbin algorithm. And you can get it to k and polylog k if you're willing to accept problem-dependent stability. So this will definitely depend on the coefficients of your Maclaurin series. And this also appears, as Nick Trevethan mentioned in his talk earlier, with extrapolation methods. And the famous one, the celebrated one, is called the epsilon algorithm. And this is a recursive scheme, and its complexity is k squared. So it's probably equivalent to Levinson and Durbin, although I don't know if there's a proof out there. Yeah. Right. So one of the reasons that Padé approximants are the gold standard is because they self-assemble their poles, and they happen to be exactly where they're supposed to be. So for q plus 1 fq's, that's particularly important, right? Unfortunately, the complexity is not competitive with the Maclaurin series, and so anyone who's interested in rigorous computation will almost immediately write this off. Okay, now another alternative in the rational world is AAA, and I'm sort of mentioning this because everyone who works with rational approximation is mentioning this today. But so unfortunately, the complexity is very large. Okay, capital K if k function samples and little k cubed for the linear algebra. But that's not sort of the only thing. I don't think that actually even the three authors would even recommend this, because this actually uses function samples, whereas everything about what we want to collect is actually at a point. So that's one alternative, but I'm not sure. So the approach that we're going to be using is actually quite basic, but it's called sequence transformation. So we're going to just use information organized as partial sums. And it's going to create rational approximations of type KK. And the complexity is going to depend on the parameters of our hypergeometric function, so max of P and Q. And it's going to be linear in K. OK, so the transformations are not opinionated. They will not actually impose a basis Okay, so they will not actually create something in the monomial basis, for example. But the numerators and denominators, effectively, they are the basis themselves. So they are going to be computed by recurrence. And that's essentially the ingredient that makes it fast. What's really cool is that they're not unencumbered. They're not encumbered by a large dynamic range. So they're particularly good for small arguments, for large negative arguments of the exponential in particular. At the very end, I'll talk about pointwise error bounds, so convergence rates for 2f0. So this is a formally divergent generalized hypergeometric function, and they're algebraic exponential, and that surprisingly was only proved in 2015, although it's folklore that root exponential is what you get when you use rational. So one of them is actually going to place the poles of q plus 1 fq's on the branch cut. The other one is actually going to fail. But it's going to permit an easier construction, so it will sort of help guide the discussion. And it's a very generic implementation. So 200 single lines of code, and it's essentially typed generically, so you can use whatever type you want for how you're representing your numbers or your arguments. Okay, so sequence transformation. So let AK be a given sequence, and what we'll do is we'll consider its nth partial sum. We'll denote that as Sn. And its limit S, or in the case where it doesn't converge, its anti-limit right here. So what we're going to do is we're going to organize S minus Sn as the remainder, and then we're going to deconstruct the remainder. So the first step in deconstructing the remainder is to assume that it actually has a controlling factor, omega, and then a constructive correction term, call it Zn. All right, so some alternatives for actually omega would come from theorems, essentially are dominating convergence. So for instance, an alternating series, we have an idea of what the remainder of that is, and so we can sort of construct a remainder estimate based on a controlling factor there. But what we're going to use is a sort of a more global property based on the sequence itself, and it's a little bit more generic. So this is a theorem of Levine and Seedy from 1981. So let the sequence satisfy an nth order linear homogeneous difference equation with coefficients, variable coefficients, that have Poincare type asymptotic expansions as n tends to infinity. Okay? Then what do? We take this right here, and then we sum it by parts. Right? So we get S minus Sn, or in other words, the remainder here. And then it turns out that all we essentially do is lower this index I from 1 to m down to 0 to m minus 1. Okay. The coefficients here are going to be different than the coefficients of the difference equation, but that will just sort of this is essentially just building the groundwork. Once we have an understanding of the remainder, then we can use this to build a sequence transformation. So the idea is we're going to approximate the limit S by some unknown quantity. We'll call it our transformation, right? Which uses information from nu running from n all the way to n plus mk, because what we'll do is we'll truncate these infinite series, which are part of the variable coefficients, which have been summed by parts. And we're going to, so we essentially have to set up a linear system to solve for our unknown, our transformation, as well as all of these corrective terms. So that would be expensive. That would be, I suppose, m cubed k cubed, if m is the order of the differential equation, and k is the sort of number of terms we take in our sort of asymptotic expansion there. But what we can do is we can say, well, okay, for PFQs, the ratio of successive terms is rational, and that actually implies that the finite difference equation is actually first order. So m is 1. That's great. Then the second thing we can do is we can sort of diverge from the theory a little bit, and we can use different forms of the constructive correction term. And so the controlling factor will be delta Sn. That's the forward difference operator, which is essentially an plus 1. And then the constructive correction terms, we can choose one as the polynomial term, right? And the other one will be an inverse factorial series with this shift gamma, which will be positive. So it turns out that, for instance, this first term right here, this first transformation, was due to Drummond in 1972, which predates the theory of Levine and Sidi. And the second is due to Shalef, who is a master's student with Sidi, and due to the law of eponymy, and Venegar's work on it is actually known in the literature as Venegar's transformation. Okay, this one actually appears more closely related to the theory. So the theory has asymptotic expansions in inverse powers, right? Whereas this is just factorial powers. Whereas this is polynomial. It's genuinely different and kind of wrong, right? But it's going to be simpler, because polynomials are simpler than inverse powers or factorials. So the idea is, instead of solving a linear system, we're going to recognize that there's some structure here. We'll divide by delta Sn, okay? And then one way to annihilate a polynomial is to apply the kth order forward difference. So we apply the kth order forward difference to both sides. We get 0 on the right. We reorganize what's left on the left-hand side. And then we end up with the kth forward difference of Sn over delta Sn, which would be here, but then we'll move it over. And then 1 over delta Sn. And then we just use like a binomial series and expand it out if we wanted to write it. And this actually shows us how this turns out to be a type n plus k rational approximation. Because each of these terms right here, a sub n plus j plus 1 is, has a power of z, right? And the numerators have Sn plus j, which will carry a little bit more weight. Okay, so this formula, if we wanted to calculate it in one shot, would cost O of k, but that wouldn't tell us when to stop, because it would just be 1. So what we need is the first k, and that costs O of k squared. So we need to show how we can do this in O of k, and specifically we can only do this for P of q. Okay, so the idea is, if we look here, both the numerator and denominator of a particular order k, right, are related to each other by applying an extra forward difference. So if we start with dn0, our initial condition, right here in terms of the n plus first term of the generalized hypergeometric series, right, we can take the first forward difference of this, right, and reorganize the arithmetic, and then write it in terms of dn0. And then we can further reorganize this in terms of Pn and Qn. So Pn is going to be this product right here of the successive factors in the numerator, and Qn is the factors in the denominator. The degree of Pn is P, degree of Qn is Q. And just for simplicity of notation, I'll use zeta for Z inverse, and n plus 2 comes from the factorial term. Okay, this is perfect, because now all we have to do is apply delta to the k to both sides, right here. And then we just expand using the finite product rule, right? But that is eventually going to terminate because our coefficients are polynomial, right? And this is essentially the key. So because both of these coefficients here are polynomial, we can terminate this sum. And the finite differences that we would apply to dn plus 1 of order 0 go into the order. And so they become k minus j, and the same thing over here. So we now have essentially a recurrence relation relating successive denominators, at a fixed n. This one can be related to of order n in O of 1 steps. And essentially we can do the exact same thing with the numerators, starting with a different seed relationship. We just have a plus 1 here instead of nothing there at all. Right? So as they're written, this is actually a max of PQ squared k algorithm, right? To calculate because of what we have to do is we have to calculate this finite difference table for every different k. But what we can do is we can start with a finite difference table and then update to go to it. So essentially update by one column and then sort of shift our finite difference table along and do only max of PQ flops to increment from one k to the next. Right. So we can do the exact same thing with the Drummond transformation. What we have to do, though, is we have to do a little bit of massaging. So first we divide by delta Sn. Then we actually multiply by n plus gamma, this Pockhammer symbol, sub k minus 1. That's going to cancel perfectly with all of the singularities in this expansion so that it ends up being polynomial again. Then we can apply the higher order difference, the forward difference, to power k. But you can see it's sort of like a weighted average now instead of just being in terms of the series elements themselves, right? That term kind of is really annoying to work with by hand, but you know, when you're sort of working out these formulas. But essentially, it gives you the right asymptotic. So essentially, we start with these similar seed relationships. We apply this increment operator to increase the order of the denominators and the numerators. And we can get linear complexity recurrence relations. This almost does everything that we need, except we still have to transfer this k into the order of the denominators. And so we can only do so much of that based on this seed relation, or this sort of relationship right here. We can only do so much of that. We still have this finite difference to take here. And then this is sort of where I left it. And then my student, I hadn't seen him in 2 weeks, and then he surprised me with this theorem, which showed that you can have this in terms of, this is a triangular relationship which relates increasing orders to higher order differences at a particular k. But not only that, but also the inverse relationship. So he used what's called the Chu-Vandermonde identity for inversion, and essentially the seed recurrence relationship, increasing k. Okay. The main reason that we love these things, sequence transformations, is this theorem right here. So this is a convergence result. It's pointwise. So for every z in the cut complex plane, because there's this function 2f0 of arguments 1, 1, actually has a branch cut from 0 to infinity. It turns out that the Drummond transformation happens to be equal to the Padé approximants. And we recover this root exponential decay in the convergence. But look what we have compared to our gold standard. We actually have something that's more powerful with this Vinegar transformation. Here it's k to the negative k to the 2/3. And compared to z, it essentially transferred some of that importance from z to k. And that's actually sort of really important. Okay. So what I'd like to do is show a little bit of nice phase portraits. So this is we have 3 proxies. We have 0f0, 1f0, and 2f0. So for 0f0, if we look at the 10th order approximations, here's the Drummond transformation. It places the poles here, and one of the roots is here. This is the Vinegar transformation. It places the poles here and then the roots here. And notice that the region where it approximates e to the z is actually much larger. And actually, this one right here actually has all the poles on one side of the complex plane and the roots on the other. So this is really good if you wanted to use this to approximate e to the z for a time-stepping scheme. For 1f0, the Drummond transformation, which was theoretically wrong, gets the poles wrong. But the Vinegar transformation gets them just right. And for 2f0, miraculously, this is the Padé approximant. So we've seen this before, I'm sure. But the Vinegar transformation also gets the poles right. And just to show you that it can go beyond the sort of low p and q parameters, here's 3f2, and here's the Vinegar transformation, again getting the pole and roots paired up very nicely on the cut of the complex plane. Right. So what did we do? We found type n plus k rational approximants for pfq very fast, right? Max pq times n plus k flops, right? What we can do as well is, because they're recurrence relations, some of them we can actually write down by hand. So for the Vinegar transformation for a particular value of gamma, we can write down the recurrence relation, and then we can show that they're Jacobi polynomials. So based on the denominators, so based on the Jacobi roots being in -1, 1, we know exactly where the poles are, and we can prove that they're on the cut, right? Even though these are not Padé approximants. Okay, and then we also have sort of these, this intuition that we're sort of working on. Right? Okay, so all of the implementation is in this package called hypergeometric functions. So thank you very much.
What kind of verification mechanisms do we have to guarantee that significant number of digits is correct all over the complex plane? I mean, you have parameters sitting in those functions, you're running Z, and preparing people to use special function scalar to take responsibility for verification.
Yeah, absolutely. So we have none at the moment, but also the license says that, like, you use this at your own risk. No, seriously. So we have none at the moment. What I can tell you is that the code is generic. So the code is 185 lines of code for the Vinegar transformation, and you can run it in floating point, you can run it in big float, you can run it with interval arithmetic, you can run it with whatever you want in Julia to give you the confidence in the result. Okay? So we don't have rigorous error bounds on this yet mathematically, but I mean deriving the algorithm for the first, the faster version of the algorithm is sort of the central part of the study.
What do you do near the branch test? Or can you do anything near the branch test so that it's accurate?
Well, with 2F1 you have linear transformations.
Right.
Yeah. No. So for 3F2 you don't have linear transformations. Yeah.
You're on one.
Yeah.
I just wanted to say that this collection of algorithms has been highly desired for a long time.
Yes.
Among other reasons, because this class of functions is more nearly closed under integration. And just purely for symbolic manipulation, we just actually really like to have this. So I like this work very much.
Oh, thank you.